guys, a very happy morning to everyone. And guys, in the previous time I just told about the manufacturing technology, each and everything, how it works and how it goes like that. I just told you each and everything. So I will just have a 5 minutes of visual. After 5 minutes we can just continue the classes. Okay, so manufacturing technology. So to deformation, everything, deformation only plastic only and metal cutting plastic, okay, cutting tool and premature teeth and everything I just told to you. And single point cutting tool and multi-point cutting tool and milling tool, turning, grinding, each and everything I just told. And generally in side part cutting only, side cutting is only cutting occurs. Paint cutting is it's less support, okay. And the shank is also there. It's the main body of the tool which holds the tool post, okay. And 0 to 1 is the side cutting edge and 0 to 2 is the end cutting edge, okay. And nose radius will be so. Nose radius should not be so sharp. If it is so sharp, it is premature automatic dose, okay. There should be a little curvature. So next thing, top face is called as rake face. In the rake face only generally chips flows, okay. But why the chips flows means you can see the top bottom and bottom bottom, but center is stable one. So top and bottom tries to compress because top no contact with each other and bottom also no contact with each other. So still top and bottom comes to the center, okay. So while it's been coming to the center, you can see area reduces and try to become stable and minimum energy become consumed. So since the top area comes contact, the area first reduces and surface region first occurs, okay. So, okay, and then down area comes, okay. So there will be difference in top and bottom area. This leads to the curling, okay. Okay, this leads to the curling of the entire thing. So that's why the chips bends, okay. I think so can understand. While chip comes out, it makes contact with the workpiece and also the cutting tool. So it may erode the workpiece also. So till the rake face angle to the chip does in contact with the both workpiece and tool, okay. So you can see side flank and this is end flank, okay. Side flank and end flank, we don't make contact with the leaves rubbing thickness slope should be, okay. Generally chips moves away from the machine tool, okay. So 3 angles are there, but 3 faces is there, so 6 angles will be. So if all this written in a predetermined sequence, it is called as tool signature, okay. To ensure the chip flows away from the machine zone, only cutting edge is exposed to workpiece, okay. Then 3 surface, rake, side and flank is sloped in 2 different directions, okay. This is okay, just normal thing, okay. So while we just write the tools in a particular sequence, it is called as tool signature, okay. By this we can understand. So you can see one tool, 6 angles. So each angle has 2 slope, 2 rake face, side face and flank face, okay, like that, okay. So at one way you can take a little it is okay. So you can see 6 angle, no radius. We will write in a predetermined sequence. It is called as tool signature, 6 angle plus nose radius, okay. Rake face, it means rake face is chips and the tool no contact, okay. We provide, okay, mainly chip and tool no contact, and side and end flank workpiece and the tool no contact, okay. And only main cutting should be contact, okay. I think so can answer. So you can see this is the ASA tool signature. Back rake angle, side rake angle, back rake, side rake, end relief, side relief and side cutting edge. Sorry, end cutting edge, side cutting edge and nose radius, okay. So BS, 2 times of ES of N, okay. Back relief, cutting, nose radius, 2 times of N surface, okay. ये कैसे American Standard Association. American Standard Association generally we do everything with respect to machine reference system, okay. With respect to machine reference system, so that's what they call it, okay. I think so. So this is a thing that I just wanted to, okay. So each and everything you can see this side cutting, this side cutting, and according to side cutting and cutting edge, I think so you would have known about each and everything, okay. So cutting first, contact first is because it acts downwards. It means whenever we just move in this direction, you can see thrust towards. This is cutting force, okay. Cutting force leads to removal of top workpiece, okay. As contact is top on workpiece, the force will always act in the perpendicular direction. So that's force equal to 0, tool no contact, okay. So So ASA American Standard Association angles can't be used for force analysis. Okay, you can see, but we need forces only weighty to measure all things, not angles. So to overcome this, the to measure this orthogonal rake system comes. Okay, it means for the force measurement we don't need angles. We need for overcoming it, we need orthogonal rake system. Okay, orthogonal system comes during investing. Measured force either appears on here and along the cutting edge. Okay, and perpendicular to the cutting force. But in ASA system, the planes are neither along the cutting edge nor the perpendicular to the cutting edge. Okay, so ASA can be used for force analysis. Okay, so you can see guys here how the angle is there, but you can see here how the angle is there. Okay, just we have just so this and to this moment there will be certain angle. Okay, both of them are same, so we see with respect to angles. Okay, so that's why over as it means orthogonal system used to compute force analysis. Okay, little different. Okay, you can see force analysis orthogonal. So this is two reference system. Okay, it shows the orthogonal angle. So first one, inclination angle, orthogonal angle, side relief angle, end relief angle, end cutting edge angle, principal angle, and nose radius. Okay, so you can see the difference. So it has been just tilted. Okay, so orthogonal rake angle and velocity rake angle. Okay, normal. Okay, so you can see vertical is this cutting edge, and you can see this one is principal cutting edge, and along the cutting edge and this one. Okay, so I think so you can see if just 1 second. So you can see if where is that one? So you can see I may be true at this. You can see this is inclination angle, this is orthogonal rake angle. Okay, so you can see the back angle, side angle, ASC rule signature, but inclination and orthogonal angle comes with the force analysis. Okay, so since ASC rule signature can be used for road lines, each and everything. Okay, so this is tan, it means used to conversion ASC tool signature to ORS conversion only. Tan I equal to cos this one, tan or either two angles, you just take whichever you are interested. Okay, so and I just told about this is lip angle, rake face, side relief angle, and okay, back rake angle, this is flank with clearance angle, this wedge angle. Okay, so theta, it means theta direct proportion 1 by strength of sharpness of cutting edge. Okay, so theta is wedge angle, also lip angle. Okay, so rake face down and this one parallel, this one will go upward. Okay, so theta 1, theta 2. Okay, this is just 20. Okay, so negative rake angle we generally don't use for measuring brittle materials. Okay, because so because the continuous chip will form and it will directly flow into the which one, the machine surface. Okay, so rubbing. Okay, so wedge angle, it is angle between the face and flank of the cutting tool. Okay, yes, definitely. So I think so you can understand. So okay guys, we can just come to the next one is cutting. So cutting entirely consists of orthogonal 2-dimensional and oblique 3-dimensional. Okay, so one is orthogonal, next one is oblique. Okay, so you can see first one is inclination angle, so we need to just tilt. So it means you can see thrust force also there, cutting force also there. Okay, so we need to have a inclination. Okay, so second one, inclination angle is also must be there, as well as the orthogonal angle. So cutting force will have 2 axes only. Okay, cutting force deflects on the x-axis. How much inclination angle is there, so that much deflection happens. Okay, hence cutting angle is also deflected downwards. Okay, so you can see cutting force and thrust force are in single plane. No, they are in different plane. Okay, so this is orthogonal cutting, x and y axis. Okay, so it means machine these force act in single plane, so then only cutting of the workpiece happens. Okay, so this is thin pipe and hollow, each and everything orthogonal plane, and here the thin and the pipe, both forces lies in the same plane. Okay, I think so you can understand. So you can see here the pipe both was lies in the same plane, and broaching also you can see like this it will be. And orthogonal cutting only 3 things you can see: sawing, it's this sawing, broaching and turning of a thin pipe. Okay, so only this 3 orthogonal 2D cutting forces there. Okay, so we generally the 3D will come, but what we are just going to do with based on some assumption we just convert to 3D, and now the oblique cutting force becomes easy. Okay, so you can see orthogonal and oblique. So during machining of the force appears on 2D. Okay, so the machining operation is called orthogonal cutting operation. Okay, sawing, broaching, turning of a oblique cutting during machining, it force appears in 3D, it is called oblique cutting operation. So except the above 3 orthogonal cutting operation, which one are broaching, sawing, broaching, turning on a very thin pipe, all other cutting operation are oblique cutting. Okay, in this force analysis is different. Okay, so that's why with some assumption we just convert the 3D to 2D. Okay, so you can see this thrust force. I think so you can see this one. So generally it means like this the cutting edge will be. So we means we just tilt it downwards, as well as just wait one sec. Okay, so you can see it means cutting force and the thrust force are in different plane, so it is not in 3D. So we just incline a little bit. You can see 10 degree and this one 10 degree. We just incline a little bit and we just convert. Okay, you can see orthogonal cutting. So assumption inclination angle is 0, cutting edge is similar to reference angle. Okay, next thing you can see here I is 0. Now see cutting force and thrust force are orthogonal plane. Okay, now we rewrite this R equal to root of Fc square plus of Ft square. Okay, so now due to 3D force system, the force analysis of a oblique cutting operation becomes difficult. Yes, so hence oblique cutting operation is treated as orthogonal. So with assumption, so generally you can see the cutting edge is perpendicular to the cutting velocity. So before it has an inclination. Okay, before it has just an inclination, but now we just made it perpendicular. You can see cutting edge is perpendicular to the cutting velocity and F equal to 0, and continuous chips forms without build-up edge. Definitely here the continuous chips forms without the build-up edge. So this is only we get right in the formula. So you can see the cutting edge is perfectly sharp and extends along the straight line beyond the length of cut. Okay, so there is no contact along the fixed surface. Okay, so you can see there is no contact along the fixed surface, flank surface. Okay, the chip doesn't flow either side. Okay, we assume the chips goes in the orthogonal plane. Okay, so all the process parameter remains constant. Okay, that's it. So just a normal thing. So you can see we just, it means in this area we just inclined it, input the inclination angle. Okay, just 1 second. So you can see here force is orthogonal system. So you can see here three, it means 3 force, feet force, radial force, and cutting with 3 forces are there. So you can see this is thrust force, and going upward is, I think so I can understand. So each and every angle we just need to take, and we need to just go. Okay, and you can see next one in inclination mean, you can see this in a 2 dimension. You can see inclination angle is 0, so we say 2D. Okay, F set, it means PZ. You can see this one PZ is upper tangent component of cutting force or main cutting force. Okay, FC. So next Fx, you can see Fx is thrust force. Okay, so Fx is cutting force or feet force. Okay, so next one Fy. Okay, F force is called as a radial component of cutting force or radial force. Okay, radial component of cutting force or radial force. So you can see feet force acts like this, and thrust force act like this, and radial force act like this. Okay, so you can see if thrust force becomes 0, contact force becomes 0. Okay, so you can see what is this one. This is side cutting edge angle. Okay, so similar to this feet force will be like this, and we just take a perpendicular line. This is feet force. Okay, feet force equal to Ft of cos theta or Ft of principal sine angle. Okay, radial force is this one. Okay, so but you can see whenever the side cutting for edge is 0, F, it means feet force equal to thrust force. Okay, feet force equal to thrust force, and radial force is 0. Okay, I think so I can answer. Pure orthogonal cutting. So you can see during machining, if inclination angle is 0, side cutting edge angle also becomes 0. Okay, this is called pure cutting, pure orthogonal angle. Okay, so you can see turning off very simple. So energy consumption. So you can see primary CO2 grower, secondary CO2 workpiece material sharing happens, atomic level breakage happens. So tool chip interface again, secondary deformation zone. So this is the main thing is the primary deformation, secondary deformation zone. Okay, so while cutting happens, it is primary deformation zone. So generally 70 to 80% of the deformation occurs here. But when it is going towards a secondary deformation, you can see just having 20 to 30% as well. Chip needed to overcome the friction. So then only chip comes out and sticks to the material. Yes, definitely. So you can see energy consumption in primary zone is so much higher. Okay. So next thing here 2% the extra energy also converted as heat. In the secondary deformation zone only here the energy is not converted. It means the most of the energy goes to conventional heat. Primary zone about 70 to 80% of the total energy is conserved and mixture breaks into. The very least amount of energy is converted into heat, about 1 to 2%. In tool chip interface, okay, rest is converted into compression converted to heat. Okay, at workpiece all regular amount of heat goes. If more goes, it is micro structural changes occurs. Okay, thermal conductivity workpiece is higher. Workpiece and thermal workpiece more, so most of the heat transfers to the workpiece. Okay, tool is less. Okay, strength less and hardness less in that case. The thermal conductivity is more. Okay, now strength or hardness also hold, thermal conductivity is less. Okay, so thermal conductivity for a tool is lesser than amount of heat generated. Okay, chips carries away mostly of the heat. Okay, out of the total heat developed, last amount of heat goes carry away the chip. So just wait 1 second. Now it's okay, I think so. So you can see, if like this it comes with, this is the shear pin, okay, shear pin, and here the normal force will be acting. Okay, so you can see this is shear pin, and here the shear force also been acting as the chips tries to move in the shear plane. Above it there is a piece, so this tries to resist the chip. Okay, so you can see shear force is perpendicular direction of this one. So when it is perpendicular, the normal force, normal stress also will be there. Okay, so you can see shear force is Fs and normal force, normal to shear is Ls. Okay, this is backup force, and normal force into AFS is normal S. Okay, and this you can understand. Now this needing to move in the chip, since energy is actually consumed into the about 2 zones only. Okay, and therefore the force appears on a 2 zone. One is primary zone, and so it's continuum. Primary zone, the force appears in the shear plane due to the resistance offered by the workpiece against the shear. Normal direction, the force appears on the direction perpendicular. This is called as backup force. Okay, and this you can see this is the shear plane, as well as this is the shearing area. Okay, so this is the width and this is the length of shear. Okay, so what is the length of shear equal to T1 divided by sine of T2. Okay? Shear area you can see is equal to W of T1 of sine of shear angle. Okay, this is the main thing, and shear force is shear stress into area of shear. Okay, so next one is tool chip interval secondary deformation zone. So in this, so you can see in the secondary deformation the chip tends to move. So this is the frictional force. Okay, but the normal force also been acting. Okay, you can see frictional force F. This force acts on the other side of the chip in the opposite direction of the chip to move. Okay, so normal force is in the force acts on the chip on the perpendicular face. Okay, next one, frictional force F is nu into 1. Okay, classical frictional theorem. Okay, frictional force is equal to nu into 1. So classical frictional theorem. So nu is coefficient of friction, B is frictional angle. Okay, so this is friction and this is normal, then this is the resultant. At the nu is friction angle, nu equal to tan B. Okay, tan of beta, angle between the normal and resultant. So nu is always less than 1. Okay, this is a normal thing. Nu equal to tan of beta, nu is always less than 1. So but in Merchant cycle this is comes greater than. Okay, so in the Merchant cycle I just explained to you. Okay, so but so this equation is valid only for nu less than or equal to 1. And actually you can see the force analysis, the cutting, metal cutting may sometimes result in greater value than 1. Okay, in case of converse analysis. Okay, so this I'll just generally explain you better. we can just see it. Okay, so you can see here the angle is theta and this angle, and you can see this is a certain angle here. This is pi by 2 minus of alpha naught. Okay, you can see m it is workpiece small element and mass, and workpiece comes down by cutting velocity. Okay, here v goes to the chip velocity. Okay, and let us consider chip element of mass which undergoes an angle displacement. So theta in time of dt. Okay, as the chip element undergoes theta, so v to vc, you can see they just goes to the circular path. Okay, wow, they just go to the circular path. So here we can't say the velocity is fixed, it may be also changing. You can see this m dv dt into minus of f of nu of n. Okay, this entire thing. So as they travel a circular path, there will be certain centrifugal force. So when you just prepare each and everything, we'll just get a certain value of nu. You can see for a coefficient of friction for this one is greater. Okay, so when while you just put in the chip thickness, you can see ln of t2 by t1, this kind of thing, just go and put it, it will be different. Okay, so you can see chip thickness highly opposite coefficient of friction and inversely proportional to alpha naught. Okay, by parameter same, because in positive and negative rectangle, which thickness of the chip is higher. Okay, negative rectangle. Okay, because alpha naught is lesser. So you can see from the equation, it is closely observed that chip thickness T2 directly proportional to nu. So T2 is the inversely proportional to alpha naught. So which thickness is high? B or A? Okay. So you can see if alpha is greater than 45, you can see put here, and you can see this 100 case. Just normal thickness, no need to confuse yourself. Okay. So you can see this is shear force, this is normal force along the shear angle. Okay. So you can see area of shear, and this one is sigma of your local stress. Okay, therefore force stresses which is actually doing the machining. Okay, so generally guys, what we do is, it means I think so you don't know about strain, it means strain gauge. So we generally use strain gauge and we don't know the whole. So we use the strain gauge. Okay, and this is really well measured. Frictional force there will be horizontal and force two force will be horizontal and normal force also. So you can see all force, vertical force is added into single force called as cutting force. Okay, so another thing, this thrust force also be there. So strain gauge dynamotor we just put and install in the device, and we will calculate it. While the tool rotates, a vertical force will hit the tool and with minimum deflection will occur. Okay, so it can be measured into feet and alternation. Okay, so we can see the force, the above force which is actually, but this can't be measured directly. So we use which one, strain gauge dynamometer, to measure the axial force, reversive force, vertical and horizontal, and which is the purpose of dynamometer. These forces are called measured force. Okay, first one will be cutting force. So you can see we generally put the strain gauge like this. Okay, after putting the strain gauge like this, we just measure the in different parameters. Okay, so you can see thrust force, you can see sum of force horizontal force is to complement the axial force. So this is thrust force and this is cutting force. Okay, so the cutting force will be and thrust force will be like this. Okay, and shear force will be like this. So we generally take that each and everything and we generally put it in a circle. Circle is so much important. This is round means, you can see this is the which tool, this is a tool, and from here to here it will be Fs, shear force, it means shear force, and next one this here to here it will be cutting force, Fc. Okay, and next one this will be the, it means this like this, it will be the friction force, F. Okay, so this is the normal force, N. So this is the radius, okay, R. Okay, radial think so you can answer. So next one, sorry, this is thrust force, and this one is the cutting force, and this is the means shear force. Okay, so generally you can see 4 forces are there. So okay, using this 4 force we just measure each and everything. So this is a frictional force, this is a normal force, thrust force, this is cutting force, and this is shear force. Okay, so you can see it means shear force, cutting force, and thrust force, and the F normal force are acting in the tip, okay, drawn by the merchant. Okay, so chip doesn't flows on either side. Okay, so R1 and R2 are equal and opposite. Okay, it's a thrust force, cutting force, RC and NS. Okay, so all points are 90, yes, definitely. So all forces are joined along with the circle beta. Okay, this is called as merchant circle. So because merchant circle taking all these forces on the tip of the tool, so he joined and he just named himself as merchant circle. Okay, so this is a thrust force, cutting force, shear force, this is friction force, and normal, two normal. Okay, suppose if you just put like this means you can see how it will be there. So this is FC, FT, and this is F and normal force, and this anything goes with the frictional. Okay, and this is Fs is what friction, it means the shear force, and this is orthogonal rectangle. Okay, so you can see this is shear angle. Okay, so next one, so this you can see is 90 minus of beta, this small thing is 90 minus of beta, and this one is beta minus of alpha naught. Okay, I think you got the point. So next one, merchant circle and here right angle triangle. Okay, so by trigonometry you can see we find all forces actual and measured one. Okay, so you can see shear force, so you can see shear force F of this is this one. Okay, theta plus beta, this is radius and this one is HA. You can see normal force you can just calculate, and this one is the entire thing. Okay, so cutting force it means this one, friction force, normal force, friction force equal to F of R of sin beta, normal force is equal to R of sin beta. So I think so you can understand. Based upon this angle we are just calculating each and everything. Okay, so you can see if just a simple thing guys, put N as F as F1 N. Okay, FCTFT, FCFT, FT each and everything, put sin cos, cos sin, sin cos, cos sin. Okay, just put plus minus, that's it. So this 4 is so much important, and based upon this we just calculate. So if alpha is 0 means you can see it directly 0. So during the day what will happen, you can see each and everything. Cutting force is equal to normal force, thrust force is equal to friction force. I think so you can see everything becomes becomes perpendicular. Okay, so merchant circle with negative rectangle. So this is negative rectangle like this. That's it, simple. So each and everything it will change to be, that's it. Okay, so next one is this one is simple thing. When this is earnest, okay, you can see total power consumption equal to power consumption shearing plus friction. Okay, you can see total power consumption equal to also it cutting force into velocity, thrust force into cutting it means thrust force velocity equal to shear force into shear velocity plus of normal velocity plus cutting force into chip velocity, chip force into chip velocity, and this is normal force into cutting velocity. Okay, you can see in this cutting force is so much important. Okay, most important, and thrust force is less important. Okay, so you can see FC into V equal to Fs into Vs plus of, which is what is this one, friction force. Okay, so you can see earnest and merchant minimum power consumption, we find shear plane position in deformation where the energy consumption is minimum. Okay, in the orthogonal angle is right to 0. So assumption orthogonal cutting shear strength on the along the shear is not by normal stress, continuous chip formation. So you can see this one is okay. So simple thing, while the problem is coming I'll just explain to you each and everything. the other thing is this one, minimum minus f2 theta plus beta minus of 1 into pi by 2 is 90. Okay, then okay guys, that's it for this video, and I'll just see you in the next video.